A damped oscillator, which is a trolley of mass 1 kilograms, is attached to a horizontal spring of stiffness K is equal to 5 newtons per meter. If the initial location of the trolley is -1 meter and it is released with a velocity of 4 meters per second and acceleration of -3 meters per second, form a different second-order differential equation. Assuming that the damping force is proportional to the velocity of the mass and acts in the direction opposite to the motion, show that the damping coefficient C is 2 newtons second per meter. Solve the differential equation to find equations of motion for displacement, velocity and acceleration. State whether the system is overdamped, quickly damped or underdamped, and use technology to graph these equations on the same axis. Bit of a windfall. This question came because one of my ex-students asked me on their imperial maths exam. So here we got the system. It's going to move back -1 meters. Its mass is 1 kilogram. Initial velocity of 4 meters per second. Initial acceleration of -3 meters per second squared. Now, the damping force will be minus c times the velocity, which is dx over dt. We're told that in the question here. And then from Newton's second law, mass times acceleration, so it's m times the second derivative of x, will be equal to the restoring force of the spring, using Hooke's law, plus the damping force. So writing that out again, the restoring force will just be k minus k times x, and the damping force we've already written down as minus c over dx dt, c times the velocity. Putting that together, we're going to get m times the second derivative plus c times the first derivative is plus kx is equal to 0, or mass times acceleration is equal to the constant times velocity plus another constant of the spring times the displacement, and that's equal to 0. So c is the damping coefficient, which we'll find in a minute, and k is the stiffness of the spring, which we're actually given is 5 in the question. So using the initial conditions, so these are all the initial conditions given in the question. This has just been extrapolated from the question. We have that the mass 1 times -3, the mass times the initial acceleration, which is -3, plus c times 4, so c times the initial velocity is equal plus 5 times the initial displacement, which is -1, will be equal to 0. If we now solve that equation, you're going to get -3 plus 4c minus 5 is equal to 0. 4c will be equal to 8, and therefore c will be 2 newtons second per meter, as given in the question. Right, so our differential equation that we're going to solve is the acceleration times 2 times the velocity plus 5 times the displacement is equal to 0. Right, so to solve this we need an auxiliary equation. This is a homogeneous equation. So it will be lambda squared plus 2 times lambda plus 5 is equal to 0. Some people like to use m here, but as I've already used m for mass, I'm using a different parameter. If we solve this, so we can just use the quadratic formula or some sort of calculating aid, and we will find that we got a negative square root, so therefore we've got complex roots. If we have complex roots, then that means we have underdamping. This is a system that which is underdamped. If this had come out to be two distinct roots, positive roots, not non-complex, then we have overdamping, and if we have a repeated root, then we have what's known as critical damping. Right, so therefore x of t will be equal to, so that the -1 here comes from this part, and then the 2 in the cos will become a constant times cos 2t plus b times sine 2t, which is equal, called equation 1. We have to now find the values of a and b. So if we differentiate this using the product rule, that will give me what's known as the velocity. So that will be the e to the minus t, and then if we differentiate that, we're going to get minus 2a sine 2t plus 2b cos 2t plus a cos 2t plus b sine 2t times the derivative of this, which is minus e to the minus t. We call that equation 2. So if we now write those out again, I should just jump to it. Okay, and then we can use the initial conditions. When t is 0, x is 0 is minus 1, and x bar of 0 is x dot of 0 is 4 meters per second, i.e. the velocity is 4 meters per second. So using equation 1, we can say that from 1, minus 1, the initial displacement will be a, because e to the 0 will just be 1, so we can just ignore that. And then this will be a, and then cos of a sine of 0 is also 0, so that makes it quite easy that a is straight away minus 1. And then from 2, we can say that 4, because the initial velocity is 4, anything with sine in we can ignore. So we're going to have 2b from here, and we're going to have minus a from here. So we've got a minus sign here, we've got an a here, this one will be 0. Okay, we already know that a is minus 1, and therefore 3 will be equal to 2b, b will be 3 over 2. So therefore the displacement will be, at each point of time, will be e to the minus t minus cos 2t plus 3 over 2 sine 2t. Now we won't ask, but the oscillating frequency of this is called omega, which is just going to be what's here, 2 radians per second. Okay, we get that from here. We won't actually ask this, but there's a bit of information we can extrapolate from this question. Okay, so if we now substitute in back into here for the velocity, because we're asked to find the velocity, so it's going to be minus 2 times my value of a sine 2t plus 2 times my value of b cos 2t plus minus. Now what I've done here is got minus 1 cos 2t and then minus 3 over 2 sine 2t, taking into account that this one here is a minus sign. Right, summing this up, we're going to have e to the minus t of the coses. We're just going to have 3 plus 1, which is 4 cos 2t. And then for the sines, we're going to have 2 minus 3 over 2, which is a half sine 2t. So that will give me the equation of motion for velocity. Now, finally, we need to find acceleration. So we've got the velocity one here, and then we differentiate this again using the product rule. So that will be e to the minus t, 8 minus 8 sine 2t plus cos 2t. When you take 2, the half will obviously cancel, and then this one will just be the same. And then when we differentiate this, we're just going to get minus e to the minus t. Right, so putting that together, we're going to get, of the causes, we're going to get a 1 here, but this will be minus 4 because of this minus sign here. Okay, and then we've got a minus 8, and this will be a minus a half, so which will give minus 17 over 2. So that's the acceleration. And then finally, we were asked to use some sort of technology to draw the graphs. So as you know, I'm a real fan of Geogebra, so I drew these graphs with Geogebra, but let's look at them from the original app, and the links I will put in the notes of this video. So if we just start this one off, we can see here the actual movement and the graphs being drawn. Green being displacement, blue being velocity, and red being acceleration. And then we had another one here where they're already drawn. Okay, and that's sort of the one I took the screenshot from. So this has been a video to show you how to form a differential equation of a damped system. And I thank you very much for watching. This is my first video of 2023, and I thank you for my student from Imperial who gave me the question. And I hope you've understood, and hopefully you will subscribe to my channel. Sorry this video is so long. Thank you very much for watching.